Okay, so it is the simpler one, and hence we are starting with this. So it is quite simple. Say I give you a situation. Let us just recap a bit of energy conservation. Suppose I am throwing a certain object from the ground level with the velocity v. Okay, and I ask you two questions. Question number one is, what is the maximum height it will go to? So it will go to some height and then it will turn back, right? Suppose there is no uh, atmospheric drag, there is no air, there is no friction due to that, there is no loss of energy because of friction. So what do you think? What is the height it will go to? That is the question. Anybody just pick up? Normal scenario, from ground you have thrown a ball up, mass of the ball is m. What is the height it will go to? Yes, guys. Fast.
Root 2 GH.
Yeah. So what will you write? How have you done it? What is the process of figuring out root 2 GH?
V square is equal to U square plus 2AS.
Okay. V square is equal to U square plus 2AS. Okay. This is also, in fact, a simple format of your energy conservation or work done is change in kinetic energy. If I multiply with half m all over, what is it? Half m v square is equal to half m u square plus half m 2as. So the half and the 2 will get cancelled. So mas, but we know ma is what? What is ma? That's the force, right? So it simply says that the kinetic energy would have changed from half mu square to half mv square, and the difference, the increase in kinetic energy would be if you have done work. Work is F into X, the work done, right? So it could have decreased it. If it is negative, it could have increased it if it is positive. So that is one way of looking at it, absolutely right, that gravity was down. The other way of looking at it, the gravity has done work, right? Because the force due to gravity, which is mg, was downwards, right? Is that clear? So this equation was something like the final velocity square is equal to initial velocity square minus 2g into h. And the final velocity square is 0, is equal to initial velocity square. Suppose it was u, I'll just write it u minus 2gh, and hence whatever answer you said is absolutely all right. Is that clear? But looking in terms of not as a kinematics question, if I look at it as energy, then we have got something, work done by gravity, we call it as something. You know what do we call work done by gravity? There's a term to it. What is it? How much is the work done by gravity? Can you tell me over here? The ball has gone from here to there. Can you tell me how much is the work done by gravity? Force into displacement, right? Mg into h, but force was downward, displacement was up, minus mgh, right? Right? That's the work done by gravity. And we have got a special name for it. What is that?
Potential energy.
Energy is negative of work done by gravity. Okay. So simply, like we have just created a name because gravitational field is around us, and potential energy is something that we have created. So if somebody else was also doing a work, some f dash, so f dash into h is properly added in the energy equations, but work done by gravity is accommodated by using potential energy. Okay. So how do we write the same thing, same scenario in terms of potential energy? Now you start paying attention because we'll be writing all the gravitational
Sir,
questions.
can you go back one second?
What?
Could you go back for 1 second?
What?
So could you go to the previous page for 1 second?
No, not required. Okay, we'll not be doing that day. You want me to go back? Yeah, this thing.
Okay, sir, done.
Okay. Okay, so the point is we have a mass here. It was thrown up with v velocity, and here, or sorry, u velocity, I'll just put it as u. And here it has become some v velocity, which if I'm saying that it is at the highest point, then velocity must be 0. We can also look at the question instead of a kinematics question that how much is the velocity, how much is the deceleration, which is the acceleration due to gravity. Instead of that, we'll say what is the total energy over here. The total energy over here is total energy. So total energy initially is equal to kinetic plus potential. So half m u square plus potential energy. Okay. So potential energy, you can take reference from anywhere, wherever you want. I can take a reference point, say, uh, uh, some d distance below it. Okay. Uselessly, I could have taken the reference point over here also. Suppose I take that. So the potential energy over there is mgd above the reference point. If we say potential energy is equal to 0 over here, then the potential energy is mgd. Now the body goes up by h height, and we don't even care that how the body has gone. Don't even care. Okay, that's the great thing about writing the energy conservation. Because if the body motion would have been like this, then writing your kinematics equation would have been a hell. Okay, so here your total energy over here, we'll just watch the body over here and comment on the total energy over here. Final is equal to half m into the velocity over there square, which is 0 square. Okay, the velocity over there is 0. Just write v square, but we know it is 0. And then the potential energy over there. Now I have to be careful that whatever was the reference level, I have to take the same reference level. Okay, so reference level was here. So from there, potential energy is mg d plus h, right? Then we'll say that in the whole motion, did it lose energy or something? We'll just inquire about it. Okay, now we'll bother about the motion. Was there any air drag? This, that. If we are convinced there was no loss of energy, then what we do? We equate the two. Okay. We say that initial must be final energy. Is that clear? Is that clear, guys? So what do we get? We get half mv square plus mg d plus h is the final one is equal to half mu square plus mgd. You can clearly see that this mgd was very uselessly taken. It gets cancelled away. Okay. And what remains is half mv square plus mgh is equal to half mu square. So if you take away the m's, it is literally the same equation, right? And your b is equal to 0. So what do you get? Instead, you get your 2gh is equal to u square, right? Right? So initial energy is equal to final energy. That is what you have been doing in the work energy chapter, right? Now comes the gravitation chapter, right? And what's the big difference? The big difference is in the work energy chapter, I was considering my zero level anywhere, that it is anywhere. So if you are h above it, the potential energy over here is of a mass which is m, potential energy is mgh. Is that clear? If you are even more above it, your potential energy over there is mg h dash. Okay, whatever that h dash is. Okay. Now This is not true at all if G itself is changing. Is that clear? Is that clear? We were taking this difference in potential energy from here to there. Suppose it is capital H, then the difference in potential energy was mg into capital H only because G was constant. We were just saying that change of energy is work done. How much would I do work to make the body go up? That is the change of energy. That much energy I'm giving. So without increasing velocity, I will apply a force of at least the weight of the body and I'll move it by capital H amount. So the work done by me will be force I apply into the movement, which is mg into h. This was the formula for work done. And this was not the formula for potential energy. Okay. And secondly, if G is changing, there is no greatness in taking the level potential energy level 0 over here. Okay. If G is changing, the work done will be a integration and all, and we rather use some formula where people have already integrated. So we'll use the actual potential energy formula. So the only point what I'm trying to make over here is potential energy formula is not mgh. Change of potential energy formula was mgh provided G was constant all over, which in gravitational chapter your distances will be very high and it will not be a constant. Are you understanding? Is that clear? This is change of potential energy formula is somewhat allowed. This is allowed provided G was constant. Is that allowed? Is it clear, guys? Is it clear? Now we are going to come at problems like this is your Earth, literally like this kind of horizon you are seeing. This is the shape of the Earth, and you are throwing a body, and maybe it is going this much of distance. The G over here was 9.8. G over there will be like very, very less. Okay. If you have gone that much of a distance, G would not be 9.8. Say it is 5 or something. Okay. Now, can you say that the change of potential energy is mgh because G itself is not same? We cannot say that. Okay. So the point is, we are going to do the same question earlier what we did, but we are going to use the correct formula for potential energy and the correct reference level. So what is the reference level? It is not the ground which is 0, it is infinity which is 0. Potential energy at infinity is equal to 0. So this is a concept which is newer and you have to get it in your head that I could have taken any level as 0. There are very good reasons to choose infinity itself as 0. Is that clear? Is that clear? Is that clear? Is that clear?
Yes, sir.
Yeah, so if this was a 0 level, if you go along the gravity, obviously, if you go above the gravity, if you take something above 0 level, it is positive potential energy. If you take it below the ground level, below the 0 level, it is negative potential energy. So no wonder that all potential energy formula everywhere would be a negative value, right? Right? Because the highest itself is 0. Is that clear? So since it's a very basic class, the point is this formula has been derived. This potential energy was due to the presence of this mass. If there was no mass, there would have been no gravity. If there was no gravity, there would have been no work done and there would have been no potential energy. Since there is mass, there is gravity. Okay, and hence somebody will require some work, some force to make it go up. This force will be varying because the gravity is varying. The force will be given by something like Gm m by r square. And since it is varying, you will not make it into x distance. You will say it is into dr, and you integrate and you get a work done formula. That work done formula which comes through integration and not simply a mgh, is the actual potential energy formula. Okay, so it is again the work done, but it is through the integration. Okay, so what is the formula? The formula is from the middle from the center of mass of the body which is creating the gravity. If I go r above from the center of mass, then at this point, if a mass m is kept, then the potential energy of that body will be equal to, yes, anybody? Minus g mm. One of the m is which is creating the gravity, one of the other m is the mass which is kept over at a certain point, minus gmm by r. So this is the actual potential energy formula. Is that clear? Is that clear? Is that clear?
Yes, sir.
Yes, sir.
So we'll be doing the same old job that total initial energy was whatever was the kinetic energy plus whatever was the potential energy, but we'll use the improved, the better formula, the newer formula, rather than using the potential energy formula as mgh, which is not a formula. Is that clear? So do a question if it is clear. You'll write the total energy here, you'll write the total energy at the other spot which I am saying. Okay. And I would say that there is no energy loss, there is no air drag and all, then you equate the two. Will you be able to do that process? Chalo, get started, okay? Let me see whether you do it or not. Okay? So I'll draw a good green earth. This is my earth, okay, even though most of it is blue. So this is your earth, and from the earth, I am throwing something up. Throwing a mass up with a velocity u. Okay? Is that clear? And I'll give you some value for that. U is equal to, this mass is having m mass, and this mass which is thrown up is small m. And U is suppose 4 root g m by r. Is the unit correct for you? Will it end up to be a velocity unit, root gm by r, unit wise, guys? What do you think? What do you think, guys? Let me see. Potential energy was equal to having a unit of gmm by r, right? Right? Or x, right? Unit wise, it was
Yeah.
gmm by x, right? Potential energy unit wise will be kinetic energy unit wise. Okay, I'm talking about the dimensions. Is that clear? Kinetic energy is what? mv square, right? Half is there and all mv square, right? So m and m gets cancelled. So v square unit wise is gmm by r. Sorry, gm by distance. So this you literally memorize, okay? That your velocity unit, your velocity square unit comes in the form of gm by some distance, okay? R plus h, this, that, whatever. Not r square and all, okay? I've seen people making a lot of error with units also. Anyways, u is given to you. It is asked if the radius of the Earth was capital R, will it reach a height of capital R? If yes, what will be the velocity? Okay, is the question clear? With this velocity I throw, will it reach a height of capital R? And if you say yes, then what will be the velocity? Is the question clear? Now what you have to do is, you have to just assume that it reaches over there. If you get a weird velocity answer like negative and all, that means it has never reached over there. Okay. And secondly, that will make your answer shorter. And then how do? You write the total energy over there. Here, what is the total energy? Write that. And write the total energy over here. What is the total energy? Apply your formula correctly and write it. And that should just do it. Okay. Do it fast. I'll give you only 1 minute and then I'll do it. Done, guys?
Yes, sir.
Cool. Who are you?
Avni,
Agni, which school?
TFS.
Huh?
TFS.
Oh, TF is also here. So nice, man. So what's the answer, Agni?
Under root GM by R.
So it reaches over there, huh? You're getting a legit answer, huh? Under root GM by R. Okay, let's see. Anybody else, guys? So let's just write the total energy initially. So we don't care what is going to happen. At that time, what is the velocity U? Okay, very well. So half mu square is the kinetic energy, right? And what is the potential energy, people? I just want to know whether you are using the right formula or not. Potential energy formula is minus G, one mass, other mass, and the separation between the mass. Separation between the center of mass of the mass. Is that clear? Is that clear? So it is lying on the ground, you can say, but it is one diameter away from the other pole. Okay. Yes, sir. I'm in a class. Yeah. Either it will be either 8 o'clock morning. It will be. You can call me, sir. I believe in. Okay. Yeah. I'm so sorry, man. What was I saying? This is the potential energy G N divided by the separation between the center of mass. Is that clear? So what do you think is the formula? What is the potential energy? Plus of a minus, potential energy is minus, so plus minus G mass of the earth, mass of the body divided by, what do you think? What will it be? What will it be? Bolo, bolo. What will it be, guys? Anybody? Separation between the bodies. Hey, people. Are you there? Are you? Speak out, man. This is not good. If you come for class, if you don't engage, it is rather you don't come for class, man. Then you have so many videos, you can watch the videos. What is the separation between M and M? What is the separation between this M and this M? What is the separation? Yeah. So R. This M is supposed to be here. Center of mass is here. That M is supposed to be there. Is that clear? So R. Now I gave you U in wonderful format so that you can have some petty calculation happening over here. So you can replace your u square with how much? M, and u square is how much? 16 times gm by r. Okay, right? Minus gm mm by r. What do you get? You get a 8 minus 1, right? Which is how much? 7 gm m by r. Is that clear? That's your initial total energy. Any doubt, guys? Now, those who did not get this or could not write this line, I'll give you another half a minute and please write this line. Unless until the line, the formula or the equation comes from your own hand, you will never be able to score. I'm telling you as plain as that. Till the time you're watching and seeing and understanding is never going to help you. You watch, you see, you understand, and you say, yeah, understood. It is never going to translate into marks. Unless until you take a little bold step and write yourself and see whether it turns out to be right or wrong. So please write those who have not written. What's the final energy over here? Say the velocity was v. We have to find the v. So we'll write in terms of v. So how much is the kinetic and how much is the potential over there? Written. Will somebody speak except for the others, except for the two people who have answered? What is the kinetic energy, guys? What is the kinetic energy? What is the kinetic energy, people? Here. Ayyo. I'll ask nothing, man. This is too much. Half mv square is the kinetic energy over there. If you can't answer that, then why are you making a teacher sit in front of you and do all of this? We can record and send it to you. This is absolutely unacceptable. And the point is, it is your life. You want to study in a certain way, you study. The greater picture is, it is not going to translate into marks or anything with respect to results if you don't engage. If you think, okay, we'll see, let's see what happens, you will have a future which could have been much better than what it will be with respect to the entrance exam, the marks over there. Okay. So please try to engage, guys. This is very disappointing. Okay, what will be the potential energy over here? Somebody?
GMM by 2R.
Okay, so minus, because the formula is a minus, G, mass of the earth is M, mass of the body is M, and the distance between the body and the center of mass is 2R. So many a times people make a mistake of calling it as R, that it is R away. It is not R away, it is 2R away, because you see the distance from the center of the mass. So that's it. This must be equal to this thing. Hence, what we'll write? We'll write this is equal to your orange thing, whatever you found. What was that? 7 GMM by R. Okay. So you see half mv square is equal to 7 plus 1, which is 8 GMM. Oh, sorry. So sorry. So this is a 7. You take the LCM, it can become a 14 by 2R, right? And on the 14, if you add 1 to it, then it becomes a 15 GMM by 2R. Any doubt, guys?
No, sir.
There's somebody consistently saying yes sir, no sir. Thankfully, at least that much sound is coming. Who are you?
Sir Shravan.
Huh?
Shravan.
Shravan. Now say more, man. Okay. V square is equal to 15 GM by R under root. The 2 gets cancelled. That is your answer. If you have any doubt in this, you will not understand escape velocity properly. If you have no doubt in this, you will understand without any issue. So ask your doubts over here now. Avni, you got your answer wrong. I hope you can figure out where you went wrong.
Sir, I took the velocity at the final to be 0.
Oh no, I had asked the velocity. Man.
Because kinetic energy at the highest point is 0.
Yeah, but I did not ask highest point. I asked R only, right?
Oh, I took it at the highest point.
Okay, is it clear, guys? Shall I give you the
Yes,
question?
sir.
Will you escape
Yes.
velocity? If any doubt over here, please ask me. The pink line and the orange line. Any doubt in those, please ask me. This line and this line. Rest is math, which I don't care. How did I write this line? How did I write this line? And why did I equate the two? Any doubt in that? Ask. Any doubt? Any doubt? Any doubt? Any doubt?
No, sir.
Okay, so in the entrance exam, there are hundreds of variations of the same question. Okay, hundreds of variations. One, suppose I was not throwing from the surface, I was throwing it from inside a duct tunnel. Then what happens? They are testing whether you know the potential energy formula when it is inside over here. When it is here somewhere, do you know the potential energy formula or not? Okay. Unfortunately, it is not a GMM by R. Okay. GMM by R is on a solid sphere and away from a solid sphere, not inside a solid sphere. So that depends on which level of entrance exam you are writing. They will test your potential energy formula. So therefore, when the class started, all the teachers, most of the teachers would have done some 4 or 5 potential energy formula. The easiest was for a point which is minus GMM by R, right? Or potential formula was minus GM by R, right? Energy will be simply multiplied with mass over there. Then due to a solid sphere outside was luckily the same formula, but inside is some other formula. Then a hollow sphere outside was again luckily the same formula. Inside is also formula of, I mean, outside was
Same
the x away, but inside is you have to take the x as r. So this is something like a lot of questions on this also, hollow sphere. Then there is disk. I don't think many entrance exam ask that. And then there is ring. Okay. So due to the ring, what is the potential energy formula? Due to a disk, what it is? If you forget also, you might not lose up on anything. But if you don't know these three, then gone may be gone. Okay. They are all based on these three formula. And luckily, if you are outside a hollow sphere or outside a solid sphere or away from a point, the formula is same. The formula is same. What is the formula? Minus GMM by how much away you are, x away you are. But as soon as you go inside, then the formulas change. Okay. So only 2 extra formula you need to know, and you are good to go for most of the entrance exams. Is that clear? Then for advanced, you should know the derivation of those formulas. Okay. That's the advanced stuff. Now let me just ask you, I'm not going to dig a tunnel and test your formulas. I'm not going to test that today. Okay, I'm just going to test your concept today. So I'm going to ask you now that it was thrown with some velocity such that it reaches, and it reaches infinity. But while it is slowing down, it was thrown with a high velocity, it is slowing down. By the time it reaches infinity, velocity has become 0. But it has reached infinity, so there is no question of this coming back. Okay. If I throw with a lesser velocity, it doesn't reach that far and it comes back. Okay. Is that clear? So again, it's ditto same equations. One orange you have to write, and one the pink line, the final. What is the energy over here? And equate the two. Again, the same thing. So the question is, how much must be the U such that it manages to reach infinity while it lost all its velocity? Okay. Is that clear? So theoretically, what is infinity is debatable or not, but the sense is that it has reached far, far, far away, escaped the gravitational influence of that planet totally, and it will keep on going with whatever velocity it remains with, and never ever come back. Okay. So write the orange line, write the pink line. And I'm not going to write, you have to write it, okay? And I will write because I'm in a online class. If it was offline class, there's no chance I would have written this. And I want to have gone to each desk and seen whether you are writing it or not. So behave that way and write it. What is the total energy over here? What is the total energy over there? And equate the two. Written anybody? Total energy at this spot, at the starting spot. It said it is U, so you can write in terms of U. Written? Written? Yes, no, yes, no.
Yes, sir.
Guys, it's not your fault. I'm telling you, it's the age. I've been seeing it for so many years. Class 9 and 10, they are so like chatting and replying and all wanting to be engaged. 11th and 12th, you feel that, okay, what the hell? I know this man. What is that? Somehow your lips get sealed. And then again, after 3-4 years, you grow out of it and you're again back to normal. But this is absolutely abnormal that one person is talking and the other one is not. If the other one is not talking, then you should not be in the conversation. So this is not a movie, right? So either you talk or not be there. Even if there is one person sitting over here, I'm absolutely comfortable. Okay, I'm not forcing you to sit. But what I'm saying is normal etiquette, which is like you are here for a dialogue, not a monologue. Okay, half, what was I saying again? Half m, what will it be?
U square plus
U
G
square
Half m, u square, yeah.
plus G
minus
M
G
M
M
by
M
R.
Not
by
a plus, not a plus. Minus g m m by r. Lovely to hear at least few voices, because that's the distance. Is that clear? Now some 1% tell me, you can tell me your name and then I'll call out and you can tell. 1% tell me this one. What's the total energy at infinity when it has lost all its velocity? Yeah. Okay, speak in unison, man. Speak. What is the kinetic energy?
0.
0.
Absolutely.
So 0.
Because it is half m v square and v is 0, right? So kinetic energy is 0, right? And what about the potential energy?
0.
Yeah, minus g m m by infinity, right? So something divided by infinity is almost 0, right? So this is here almost 0, right? Is that clear? As such, it is a theoretical thing that what it has reached infinity and all. Okay. Now you equate the two. So when you equate the two, what do you get? You get this orange thing is equal to 0, right? This much is equal to 0 if initial is equal to final. So that ends up being half mu square minus g m m by r equal to 0. So if I take it on the other side, that means half mu square is equal to gmm by r. Mm gets cancelled, 2 goes on top. Your u is equal to 2 gm by r under root. So this velocity is called your escape velocity. Is that clear?
Yes, sir.
Is that clear?
Yes, sir.
Yeah, yes, sir.
Okay. So if you throw with lesser than this velocity, what is going to happen?
The body will come back
It'll
down.
It won't go to infinity. It will go somewhere else, less than infinity, where the velocity will become zero. So it will stop over here and then it will return. If you throw with more than this velocity, obviously it just keeps on going away, right? And the velocity, like after reaching a certain point, it never decreases, keeps on going with that extra velocity. Is that clear? So for Earth, we can do a quick calculation of this by using the fact that gravitational field on Earth is equal to Gm by R square. This everybody knows, right? Right?
Yes, sir.
Yes.
Yeah. Because we say that weight on Earth is mg, but we know that if we have to use it properly, then the weight on Earth is the force with which Earth pulls the mass, which is gmm by R square. So that means this G was nothing but Gm by R square. Is that clear? It is called
Yes,
the
sir.
field. Okay. So the G calculation is Gm by R square. So we can somehow use it over here. It is so close to that. The R square is not there. So what I can do is I can say it is a 2Gm. I place a R on top and divide with a R. So I get a R square. So that I have little less of a hassle instead of putting the G value and the mass of the Earth and the radius of the Earth. Radius of the Earth I'll have to put as such, but I don't have to put the G and the M value now. So this is roughly equal to, I'll just take it as 9.8 as 10. It is roughly equal to 2 into 10 into R. Anybody? People know what is R?
64,000 or 6,400.
6,400 kilometers. Okay. 6,400
Yeah.
kilometers. Okay. Okay. So such nice numbers, right? So 64 has got a under root, the two zeros over there. Then this power 3 is there, but then extra 0 is there. So it becomes a power 4. Okay. So that 64 will give you an 8, right? Right? These two zeros is going to give you a 10, right? On under rooting, right? And then 10 into 10 power 3 on under rooting is going to give you another 100, right? Into a root 2. Is that clear? Meter per second, because that was the unit I have used. Okay, this was meter per second square, and this was meters. The meter square per second square on under rooting gave you meter per second. Is that clear? So this 1000, I can just eat up that 1000 and call it as kilometers per second. Kilometers per second. So I just eaten up the 1000. So the answer is 8 root 2 roughly, right? 8 root 2 roughly. Root 2, if you wish, you can write as 1.4. So 8 into 1.4 will be like 8 into 0.4 will be like 3.4. So 8 plus 3.4 roughly 11.2 kilometers per second. Okay. So insanely high velocity if you throw with, and suppose there was no atmosphere, then the body can escape. So that's your escape velocity. Any doubt, guys? Any doubt?
No, sir.
No doubts. Then we'll go on to the Kepler's
Yes,
law.
sir.
If any doubt you ask me, I'll wait for 30 seconds. Any doubt? Ask. Okay, what the hell? If it is happening, let me just get convinced. There's a planet which is twice the mass of Earth. The radius is same as radius of Earth. Okay? And the mass of the planet is twice the mass of Earth. Is that clear? Is that clear?
Yes, sir.
Yeah. So calculate the escape velocity, and homework question is, if I have thrown with half the escape velocity, how far will it go? Two parts. One part you do right in front of me because that is damn basic what we have been doing. Calculate escape velocity. Once you have done that, part A, as homework you do, that if thrown vertically up with half the, don't look at the board, start doing, calculate the escape velocity. If thrown up with half the velocity in part A, so I'm depending on the right answer of part A, find or calculate I'm just hoping by the time I end the second part, you have done the first part. And I'm not looking at what I'm writing. Done, guys?
Yes, sir.
Okay. What is it?
2 root GM by R.
Give me some numerical value. Or in terms of so much into escape velocity of Earth. Or you can use escape velocity of Earth as 11 root 2 kilometers per second. What do you think? It will take more velocity or less velocity to escape?
More.
More.
It's more massive with the same radius. It has got immense gravity, I feel. Right? Right, guys?
Yes, sir.
Yes, sir.
Okay. If the radius was also 2r, then if the radius was also
Same. It
2r,
would be
then
the
the
same.
density is not that great. Hmm?
It would
The
be the
radius
same.
was also 2r. No, no, not same and all. Okay. You have to actually calculate. If it comes same, because yes, yeah, we have gone up a bit. So that way, yeah, the 2 and 2 will get cancelled. Okay. But logically, you'll have to think through it, that why it comes same. Yeah, done, guys. Done.
Yes, sir.
Done. How much it is?
22 kilometers per second.
Huh?
22 kilometers per second.
22 into root 2, you are saying? Or 22 itself? I don't know, I'm just asking.
Just 22, sir.
Okay, so guys, you can do by two ways. One by basic, by writing the total energy over here. Total energy over here will be half m u square, where u is
Sir, even I'm going.
what? Okay. Minus the
Even I
potential
got-
energy over there. The potential energy over there is g, mass of the planet, which is twice the mass of Earth, into mass of the body, which is m, divided by radius of the planet, which is fortunately the radius of Earth. Okay. This total energy ultimately on reaching infinity, there the total energy is equal to 0. So this you will equate it to 0. And when you do that, you get your u square is equal to 4 GME by RE, right? Right, guys? Right, guys?
Yes, sir.
Yes, sir.
Or you could have used the formula itself, that escape velocity is given by. I would not recommend you to use formula because formulas are hardly used anywhere. Okay, is equal to under root 2. We just found it out, right? 2g into mass of the planet divided by radius of the planet, right?
Yes,
Is
sir.
that clear? Is that clear?
Yes, sir.
So this has a formula and this has a concept. You see, the concept is not very far away from the formula. It is just one extra line. So highly recommended. Okay. So any which way you'll get a under root of 4g mass of the Earth divided by radius of the Earth. Is that clear? Out of which, if I separate it out, then it is root 2 into root 2 g mass of the earth divided by radius of the earth. This part is already given as escape velocity of the earth, right? So your answer for this planet is root 2 times escape velocity of earth. Is that clear? And if you use the value of escape velocity of earth as 11 root 2, so 11 root 2 into root 2 gives you 11 root 2, which is 22 kilometers per second. Is that clear, guys?
Yes, sir.
Yes, sir.
So do the other part yourself, that the velocity is half of it, half of you found. That means u is given as how much? U is given as how much? Root of g mass of earth divided by
2.
radius of earth. If this is the velocity, part 2, okay, instead of this one, half of it, okay. So u was equal to 2 root g and mass of earth divided by radius of earth, half of it, so 2 goes away. So if this was the velocity, what is the height it will achieve? Okay, you do it at home. That means you have to write properly the total energy at this spot also. Okay, is that clear? Height from the surface is arc, that is always a bluff, okay, above the surface. So from the formula, you'll get the height from here, right? And then reduce the r. Are you understanding? So this is like a common cheap bluff what the entrance exam will always throw at you. Okay.
Mentioned if it was 2R, it wouldn't be the same as Earth.
No, it would be same. Then because it would be same. Okay, it's just because the 2 will get cancelled, it will be same. The point is, if it was 2R, it is less dense than the Earth. Okay, but it is same as what you were throwing from the Earth this much above. I'll tell
Okay,
you what
sir.
I mean. Okay, I'll tell you what I mean. This is the Earth, right? Hmm?
Yes, sir.
Now, if there is a planet which is twice the radius of Earth, 2R, and twice the mass of Earth, okay? Then you're throwing from here, that is helping you out, okay? This planet has got less gravity, okay? Why it has got less gravity? Because when you
It's less
increase
dense.
the radius by 2 times, the volume increases by how many times? If you increase the radius by 2 times, the volume increases by 8 times. So the mass should have increased by 8 times, but it is just increased by 2 times. That means it is quite a less dense thing, right?
Yes, sir.
Okay. So, but the escape velocity from here will come the same because it is as good as, yeah, the calculation, the escape velocity will come the same. Okay. Because your potential energy part will come as minus g 2m m by 2r. Okay.
Got it, sir.
So even with double the mass, if you are this much away, it is same as with half the mass you were this much away. Okay.